Okay, this is a nice review paper, which means it's quite long and obviously has lots of very useful references. And as you know, my style by now, probably, I tend to be very brief. I just pick topics that I think are important and I want to report them to you, but I don't want to go into a long series of lectures on each topic. So, this is about practical paths towards quantifying and mitigating agricultural methane emissions. Methane is tricky because it's hard to make estimates because it's not as easy as CO2 in terms of long lasting well mixed gas. You measure it in one or two places, and you get a good estimates of the hemispheric concentration. Methane tends to be very local and it's easily oxidized into carbon monoxide, has a time scale of about a decade, but it's very powerful as a greenhouse gas, 25 times or more as powerful as CO2. So we want to really understand it and quantify it and then find ways to mitigate the emissions as well. So the review here summarizes the rapid advances in direct practical methods to quantify and reduce agricultural methane emissions worldwide. Major tasks are location, identification, quantification, and distinction between different specific sources, and they are often multiple emitters such as manure pools, animal housing, biodigesters, and landfills being co-located, so you don't know exactly what amount is coming from what. Emissions reduction facilitated by developing methodologies for locating hotspots is the least cost choice action, especially from manure stores, biodigesters, and from controlling biomass burning, which is a big part of agricultural practice as well in many countries, as well as using that for cooking, etc. in some poor countries. Agricultural methane can also be used to generate electricity or in appropriate circumstances can be destroyed by oxidation. As I mentioned, it may be possible to cut North American, East Asian, and European emissions sharply and rapidly. So in a global mitigation effort, those are good targets. Then in Africa and South Asia, emissions from crop waste and food waste in landfills, also a source of air pollution, can be sharply and quickly reduced. So different sectors, but again a reduction potential. Chemically that means something else, but anyway, globally cutting total annual agricultural and waste emissions by a third would demand reductions of very approximately 75 teragrams per year. Very approximately, because as I mentioned, methane is always tricky. Apportioned by source type, national cuts might be 30 to 40 teragrams per year from livestock and manure, 5 to 10 teragrams per year from rice cultivation, and 20 teragrams per year or more from specifically agricultural waste. Rice cultivation always gets a lot of attention, and so does livestock, dietary changes and so on, or how to better bring up livestock, but that's a different topic we have discussed elsewhere. Rice cultivation also we have discussed elsewhere in terms of ways to reduce irrigation, flood irrigation, and so on and so forth. So as I said, I'll be brief. I'll show a few figures, we'll make some points, and then jump into the conclusions. Introduction then. Agriculture is the largest anthropogenic source for methane. Failure to reduce global agricultural methane emissions will put the goals of the Paris Agreement out of reach, the 2.2 degrees C or 1.5 degrees C by 2100. The United Nations Food and Agriculture Organization has called for sharp reductions in gross agricultural emissions of methane, while Global Methane Pledge has committed over 150 nations to cut 30% in gross anthropogenic emissions by 2030. The first part of this review summarizes the current growth of atmospheric methane, placing it in the context of climate change. We discussed rapid advances in quantifying agricultural methane sources and consider ways to control and mitigate methane emissions. Finally, we suggest possible pathways and targets for reducing emissions. So it's not so much as conclusions, but pathways for action. Methane annual change in parts per billion per year, as we know, it's a trace gas, even orders of magnitude smaller than CO2, which is in parts per million. So here you see that it has large variations and not monotonic trend like CO2. Annual global increase in atmospheric methane 1984 to the present, which is 2024. In 4 decades, only 2004 has seen a significant decline. And annual growth in 2021 was the highest ever recorded. So you have to go back and see why that was. Many factors can contribute. Here is the longer term trend. So you can now see that there is a trend, but not as monotonic as CO2. These are also estimates. Methane growth as recorded at the South Pole, the world's most remote observing point. So it starts in 2000 and goes up to 2024 or so. So it's not a very long time series. So you can see even in that you had relatively no growth for a few years, and then it has taken off again. Okay, so this is the delta carbon CH4 as recorded at the South Pole, the world's most remote observing point again. So the isotopic composition of methane is changing. In CO2 we look at delta C13 to C12, because if you burn fossil fuel, organic matter has depleted C13 compared to the atmosphere, so you have a drop in delta C13 to C12 ratio. Here delta C of the methane is also dropping, which indicates more of a biological source being the contributor, again because the C13 is depleted. Methane's recent growth rate and isotopic shifts. Then the amount of methane in the air is growing rapidly. After an approach to steady state, the increases since 2006 were unexpected, and high growth rates since 2020 have been remarkable. We don't know if it will start dropping out again or flatten out. The record of the U.S. National Oceanic and Atmospheric Administration, NOAA, clearly shows the strong growth pattern since 2007, when the period of equilibration in the early 2000s ended. So if you look at a longer term methane record, it has quite a variation that's not all fully explained. Plus, remember that methane is not as well mixed as CO2, so the local, regional specific sources and sinks are quite varied. When you do global averages, you have to be careful. Accompanying the recent strength, methane's isotopic shift to more C13 depleted values, which began in late 2006 and 2007, is reversing a centuries-long carbon enrichment trend. This suggests that methane's current growth is dominantly caused by increases in emissions from biological sources. Methane emitted from fossil fuel and biomass burning is comparatively rich in C13 and drives delta 13C in CH4 positive upwards in figure 2, while biologically sourced methane emission from wetlands, agricultural ruminants and bio-waste disposal in landfills, sewage, etc. drives delta C13 in CH4 negative downwards, delta 13C, delta O18, delta C13. So delta C13 methane in methane from the South Pole is shown here in figure 2 that we already looked at. Essentially, fossil fuel domination versus biological sources appears in the delta C13 of the methane. Okay, we have to understand the emissions also, because we are using them in the emission scenarios. The older ones were called representative concentration pathways. 2.6 is of course the most benign one in terms of hoping to reach less than 2, or hoping to remain below 2 degrees C by 2100. So this is the forcing. So the isotopic changes also affect the effective radiative forcing. Remember, methane is a greenhouse gas and it traps outgoing long wave energy, which results in additional energy trapped in the Earth system, which is what we call forcing. So this is observed CO2 versus methane, and then the various scenarios. So the scenarios are all here, they are made up, various details are involved, but if you just focus on the observations of radiative forcing from CO2, you can see that it has been this is very hard to separate the two, but greenish is the methane, but you have to look at the circles here. So they are all together up to about 2010, and then you can see that CO2 dropped and then picked up again in terms of watts per meter squared, and methane has taken off, and that's approximately consistent with the isotopic changes as well. There are details you can read in the paper as to why that is. I'm not going to go into it, but just to report that it is being observed to increase recently, and the biological contribution, biogenic sources, is growing up. So growing, not growing up. Millions of tons of methane per year for these various scenarios. You can see that SSP2 4.5. I have discussed scenarios themselves elsewhere. You can look up shared socioeconomic pathways. 2 is the pathway number, 4.5 is corresponding radiative forcing in terms of RCPs, and SSP1 2.6 is the most benign, 1.9 is even better in terms of trying to stay below the global warming targets of 2 degrees, 1.1, and so on and so forth. So obviously these mean that for the future it's not just CO2 that we have to worry about, but all greenhouse gases. In this context, the methane, some rustling sound here that I want to avoid. Okay. What else shows? This table shows percentage increases for illustrated source categories over the half-century period of 1970 to 2021, and relative share of the source category to the total methane emission in 1970 and 2021 respectively in Edgar inventory, which is one of the inventories, so you can look it up in reference 14. Increase since over 1970 to 2021 in terms of relative contribution to total emission. So enteric fermentation, manure management, rice cultivation, emission from biomass burning, incineration and open burning of waste, and other anthropogenic sources like power production and so on and so forth, which is not within the biomass burning. So you can see that anthropogenic sources here have increased, and emission from biomass burning has increased significantly. Enteric fermentation shows an increase, and this is the relative contribution. 1970, what did they do, and 2021, what did they do? Enteric fermentation is almost the same. This one has increased a little bit, 0.3% to 0.5% over 1970 to 2021. And incineration and open burning of waste has actually dropped just a tiny bit, but other anthropogenic sources have increased by 10% over this period. At 1970, it was at 47% in terms of total contribution to total emissions, but by 2021, it was 57%. Okay, so if you look at it another way, source apportionment of global agricultural waste global agricultural and waste methane emissions, again from the Edgar estimates, methane emissions in teragrams per year. Usually CO2 we think of gigatons per year, but methane is in parts per billion, so when we convert it you end up with teragrams as a better unit. So here you are looking at again at contributions from enteric fermentation, rice cultivation, emissions from biomass burning, manure management, incineration and open burning. Blue contribution from enteric fermentation is large and continues to grow. With growing economies, often meat consumption goes up, and enteric livestock meat consumption increases the production of meat and enteric fermentation, and rice cultivation has dropped a little, but not enough compared to previous earlier periods of 1970 to 1985 or so. Manure management remains almost the same. Incineration and open burning of waste is somewhere here, and emissions from biomass burning is also a tiny bit, but each piece is important. What are the sources then? Emission hotspots: 1, biomass digesters; 2, manure management; 3, crop waste and grass fires; and rice fields, burning, converting or destroying agricultural methane; feed additives to livestock, and there are now certain algae that you can feed the cattle to reduce their fermentation or emissions of methane. Alternative approaches for methane mitigation: disease control, breeding, and good farm management. Open range versus intensive livestock management. So industrial production tends to just put them in a cage and then feed them, fatten them, and so on. Methane is not a consideration there. Nitrous oxide, interaction between methane and N2O mitigation, and landfills. So each one of these topics has a detailed discussion in the paper that I'm totally skipping so that we can just jump to some other points. Human diet and health, reducing obesity in terms of reducing emissions. Reducing obesity and increasing plant-based human nutrition will probably cut methane emissions, both from agriculture and landfills, provided crop waste and fertilizer are well managed. Global overconsumption of food, which is the obesity epidemic, is damaging to public health. Both obesity and airborne particles from crop waste burning are major causes of illness. These factors are increasingly important in Africa, the Middle East, and South Asia. And then there is further detailed discussion that I'm skipping, but obviously changing to plant-based diets is not very easy. Culturally, meat consumption is built into a long history of humanity, and many cultures get their protein from meat, so we have to be careful about nutrition as well. Okay, so just to run through some mitigation targets and methods. Mitigation focus can be obviously one of the sources we looked at. Manure stores, in building methane, biogas system leaks, in pasture methane emissions, livestock, low CH4 breeding, rice field emissions, crop waste smoke, and so on. And detection and quantification is mentioned here, how you can do it. Continuously running instruments, in situ measurements with unmanned aerial vehicles and SUVs. I should look up in this paper. I forgot what SUV was in this paper. Let's do that right now. I hate to do this in real time, but since I forgot what it is, it's unfair to leave it hanging. Obviously, yeah, sport utility vehicle is basically that means you are running SUVs instrumented to measure methane. Hopefully they are electric vehicles and the batteries are charged with renewable energy. Okay, target mixing ratios are mentioned. Concentration, basically. Reduction or removal methods can be thermocatalytic oxidation, biomethanotrophy, rigorous control of the leaks and gas tight covers on the tanks, better pasture management, animal health, feed additives, herd breeding and management, better crop management, alternative use, waste use for energy, for example, and so on. There are other options, and cost of reduction or removal, moderate if solar and wind powered, low and profitable. So they have taken all these things into account to make sure that actual mitigation happens in terms of the energy used as well as methane reduced in terms of sink, strength of the sink, or emission rates, which is the same thing. Detection and quantification, local area methane measurements, again the sources that we already mentioned, manure lagoons and tanks, in buildings, cow barns, biogas systems and digesters, outdoor feedlots for industrial animal meat production, animal and in-field measures of methane emission from livestock, rice fields, crop waste fires and landfills. And detection systems, as before, depends on what kind of instruments you use. Point source detection ranges are given, access and time scale, and cost of detection and quantification, speaking relatively low, and so on. Okay, so very nice detailed paper. Why am I being so brief? Because unless you read all the text, these don't make much sense, relatively speaking. So point source here, for example, detection ranges in kgs per hour, 0.1 and upwards, 0.02 at less than 10 meters, 0.1 upwards, and so on. And here access and time scale, good access, 24/7 monitoring for manure lagoons and tanks, whereas access may be difficult for rice fields, and so on. Okay, satellites obviously also can play a role in some cases. Mitigation options, which is one of our main goals to, quantifying is very important, of course. Mitigation is even more important, but quantification is needed to see where mitigation potential is high and where resources need to be invested. So mitigation options for the various targets we looked at, from biodigesters to human dietary change and obesity reduction. So various mechanisms: leak reduction, emission reduction, thermo or biocatalysts for greater than 100 ppm per year, just in terms of it's a very tiny amount, then it will not work. Regulatory control, alternative management changes of rice fields, lowering emissions with feed additives, disease reduction, low methane breeds, leak reduction and capture, lower ruminant population, and so on with dietary changes. Probable costs here just given as low, moderate, negative, which means you get net profit, etc. Potential mitigation, again approximately some teragrams per year or greater than 10 teragrams per year. Sometimes uncertainty is high because the probable cost is also low, we should try it anyways. And much greater than 10 teragrams per year, that's for landfill potential mitigation. With human dietary change and obesity reduction also, we could get much greater than 10 teragram per year mitigation. So these are possible. Some are rapid, some will take decadal time scales, and so on. Okay, what are the practical targets to mitigate agricultural emissions? There are many attractive targets, as we saw in table 2 already. We looked at all these mitigation foci. These include emissions from manure, leaks from biogas systems, using waste gas for fuels both directly from tractors on farm or via conversion to methanol and hence liquid fuels, and even synthetic aviation fuel. Life cycle analysis needed again. Improved management strategies, low methane animal breeding and methanogenesis inhibitors could significantly reduce emissions. With favorable energy supplies, methane removal is possible. Marginal abatement costs of tractable emissions from manure, biodigesters and crop waste are likely to be comparable with mitigation costs for gas and landfill industry emissions. In practical terms, as illustrated by the proposed US Emit Less Act, regulatory carrots or subsidies are more likely to succeed than sticks or penalties. Okay, what are the conclusions? In the context of efforts to reduce both long-term effects of CO2 and near-term forcing by methane, controlling agricultural emissions of methane should be an urgent part of national commitments to limit climate warming. Many actions to cut methane emissions have strong co-benefits for public health, so the economic costs should include those as well when possible. The costs of mitigation are hard to assess, as there is a wide opportunity for technical improvement to cut costs dramatically. Though agricultural methane emissions are widely seen as intractable, much can be done to make them tractable. Effective mitigation of agricultural methane emissions will need determined policy attention coupled with sustained implementation of that policy, but may not necessarily be expensive. Efforts to reduce emissions will be encouraged if cutting measured methane emission is seen as important in nationally determined contributions to climate mitigation, the NDCs. The alternative Compensating for methane emissions by CO2 removal is unrealistic and seems wrong intuitively. It's far better to cut methane emission itself. The gases are very different in their radiative forcing timeframes, and balancing the forcing from a small mass of methane would mean removing a much larger mass of CO2, right? CH4 has a huge global warming potential, so any methane reduction you do is equivalent to reducing a lot of CO2. Broad tasks include better measurement, identification, location, and quantification of emissions, emission reduction, cutting or stopping emissions, methane destruction or removal, and use to produce energy where emission destruction is not feasible, and human diet changes. Measurements, we already mentioned a few things like UAVs, SUVs, satellites, in situ measurements, and so on. Emission reduction is the least cost choice. Opportunities we saw already in table 4. The most obvious immediate targets are cutting leaks from biodigesters and biogas chains, and also from manure tanks, ponds, and lagoons, so cattle, pig, chicken manures, and so on. And reductions are merely guesses, but collectively over the period of to 2050, it's possible that determined regulatory intervention may lead to total worldwide reduction of agricultural emissions by perhaps 50 to 60 teragrams per year or more. Okay, so relatively speaking, that would be a good contribution to overall climate mitigation, greenhouse gas reductions. Destruction, methane oxidation to CO2 removes most of the global warming effects. In high methane air enclosed cattle facilities such as cattle barns, where mixing ratios are high in terms of 50 to 100 ppm of CH4 compared to parts per billion levels, methane destruction may be feasible when it's that high concentration. It's just literally like capturing methane for biogas, and so on. So obviously destruction is possible, and remember, methane is 25 times more powerful than CO2, so that conversion still pays off even if there is CO2 leak. Human diet changes on a wider scale, considering human rather than cattle feed, evidence-based changes to human diet. For example, encouraging better public health by cutting obesity will reduce per capita food consumption and hence both agricultural production and landfill inputs in terms of food waste. But obesity remains massive epidemic, and people try so many things to lose. There are genetic factors, and often poor people may look fat, but that's because they are getting poor quality food, which makes the body crave for more food. So there are some details we have to worry about on how to bring about obesity changes. The benefits to health are obvious, so can that be the way to incentivize obesity reductions and hence methane reductions? The real test for greenhouse gas policy is direct atmospheric measurement, as we saw, when a multi-year section, say 5 years of the methane growth curve, has entered a convex decline, and when the delta 313 of the CH4 curve reflects a cessation of inputs from gas, oil, and coal industries, and also an end to growth in total biological emissions, both anthropogenic and natural, then there will be hope for abatement of methane's climate disruption. The task of reducing agricultural methane emissions is complex and challenging, obviously. There are no magic bullets, but rapid real reductions, though difficult, are both necessary and possible. Okay, so it's a relatively short summary, barely 30 minutes, but the paper is quite long and very useful with lots of very nice references and details on measuring and so on. So please go and read the paper if this topic is of interest to you, but I'm going to leave it here. Okay.